Hi guys, today we are going to talk about a very important topic, equilibrium of rigid bodies. We have been preparing for this in the past few lectures, actually basically from the beginning of the semester. So this is a very important lecture. The chapter that we are going to cover today is to finish up with all the tools that we need in order to tackle the task of equilibrium of a rigid body. Let's talk about the equations of equilibrium. Equilibrium. Let's say we have a rigid body. In order to guarantee the equilibrium of this body in the 2D plane, we need to guarantee that it doesn't move with acceleration in the x direction or in the y direction, or that it doesn't rotate. So this, in order to guarantee the equilibrium, there should be no translation, no movement, no movement. In order to guarantee that there is no acceleration in any direction, we can decompose all the motion in x component and y component. So here the body is supposed to move in with acceleration in this direction and in this direction. So the combination of those two motions produce this motion on the plane. And we can talk also about the rotation. There should be no rotation, no rotation, no rotation in order to guarantee that there is equilibrium. So in order to guarantee that there is no rotation and no translation, what we have to verify are these three concepts. No forces in the x direction, no forces in the y direction, and no moments. So as equations, this will be that if there are forces applied to the body, force 1, force 2, force 3, force 4, if you take all the components of all those forces in the x and y direction, y, x direction, x, y direction, y direction, if you take the summation of all the components in the x direction, all that summation has to be equal to 0, so there won't be acceleration in the x direction. So there will be equilibrium in the x direction. If you take the summation of all the components in the y direction and all that summation is equal to 0, so we can guarantee that there is no acceleration in the y direction. And then if we take the summation of moments of all the forces around any point, doesn't matter what point, because remember that the momentos are free vectors, you can put it anywhere. So once you have the summation of moments with respect to one point and you have equilibrium that doesn't produce rotation, that equilibrium has to be good about any point. If the body doesn't rotate about a given point, it doesn't rotate about any point. So you just express that as summation of moments, I would say, in the z direction, or we can say just summation of moments, because we will be working only on the 2D plane. The summation of moments, if that summation of moments is equal to 0, then we guarantee that there is no rotation. No rotation. So those are the three equations that we have to verify in order to guarantee the equilibrium of a body or rigid body in the 2D plane, equilibrium in 2D. So we have three equations. If we have three equations, then we can solve for three unknowns. We cannot solve more than three unknowns in a problem of equilibrium of a rigid body in 2D. Okay, so let's take a look at some examples that we might encounter examples that we might encounter when we study equilibrium of rigid bodies. These, for example, these are typical problems that you might encounter. In order to analyze these problems and study the equilibrium, we need to know how to deal with the supports, what to do with this, what to do with this, how to handle this. So before we start analyzing these problems, let's take a look at how to deal with the supports, how to deal with this kind of stuff. Let's take a look at supports. These are various kind of support. There might be some others, but this is kind of like the general idea about all the supports that you might encounter. Others, it's gonna be very similar to this. Let's take a look at them one by one. The first series of supports that you see here are supports that only create one reaction in one specific direction. This is also supports on rollers or a rocker or a frictionless surface. If you get one of these supports, then let's say this is the element and the support was here, you can imagine that if this, let's say this is subject is connected to a rigid body here, and then if this body tries to move horizontally, this support cannot oppose to that kind of motion. This support will move. So that means that this support is not able to produce a reaction to oppose to that kind of moment. So there is no force in this direction produced by this support. But if this support tries to apply force down, then the floor down here is going to oppose to that force, and it's going to react with a vertical reaction. So when you're going to analyze this kind of support, you are going to replace this support by a force that is going up. You don't know what is the value of that force. You're going to find it. It's going to be one of your unknowns, but you know that the reaction is vertical. There will be no reaction horizontal because, as we said, if you try to move the support horizontally, the support is going to move because it has these rollers here that don't oppose any resistance to the motion in the horizontal direction. So any of these supports here are going to behave like that, just a vertical reaction. This one here is a little different of the other three because this one can oppose force in the vertical direction going up as well as in the vertical direction going down because it has the restriction on both sides of the roller. So it could be up or down, same thing. And on the other hand, in the other three, they only apply reaction in the vertical direction going up. Because if you try to, if you have the support like this, let's say the frictionless surface, and you try to lift up this, it's going to lift up, no problem. It's going to lift up, and there is nothing that the floor can do in order to avoid that the body is lifting the leg like that. So the reaction in this case will be only vertical going up, no vertical going down. As in the case of this roller can apply reaction up or down. That doesn't affect us much because since these forces are unknowns, when you set up the equations, you can put the direction, the sense of the force, you can put it in any direction you want. And at the end of the calculations, if you find that the result gives you a negative sign, you know that what the sense that you assume was wrong. So you just put it in the other direction. So in that sense, when you replace a support with a force, it doesn't matter the sense in which you put the force. You can put it up or down, and at the end, the result will tell you if your assumption was correct or if it was incorrect. So let's talk about this kind of supports. In this kind of support, the one on the left is a short cable. So if this is your, there is, let's say this is part of a bigger element, and you have a short cable here, this cable is only able to produce tension. So you are going to replace this cable by a force in the direction of the cable. So you will be given this angle here. So this angle, say 40 degrees, 60 degrees, whatever, is usually known. So the direction of the cable, the direction of the force will be given by the geometry of the cable. And the only unknown that you have here is the magnitude of the force. So it's kind of similar to the first set of supports, only that the angle in this set of supports was 90 degrees with the horizontal. In all those cases, it was a force even going up or going down at 90 degrees. In this one, is a force that has a known direction, but it's arbitrary, whatever the geometry of the problem is. Like in this case, I said here 60 degrees, could be anything, but it's known. The only unknown is the magnitude. Same thing as in the initial set of support. This, the only unknown is the magnitude, not the direction. Eventually, the sense is also an unknown, but it's just the sign that you get at the end of the calculation. Let's see the third set of support. What happened with this support? Let's see the color. You have a color like this, and then this. In this case, this color can slide easily in the direction of the rod, so there is no force in that direction. The force cannot, there is no restriction to the movement in that direction. So this force that doesn't exist. The only force that can this rod exert over the body, which is, this is like part of the body. The body will be here somewhere, right? So the only force will be in this direction perpendicular to the rod. So it could be like this, or it could be like this. That will be the force perpendicular to the direction of the rod. In that case, it's similar to the previous case. It's only one unknown, is the magnitude of the force, but the direction is given. It's 90 degrees to the whatever direction has the rod. In, let's say this is 45 degrees or whatever, it's gonna be probably given. So the direction of the force is known. With the geometry, you're gonna know because it's perpendicular to this rod. So the only unknown will be the force, the magnitude of the force. The sense will be also unknown, but as I said before, if you don't know in what sense it is, so say you have here the color like this. So you remove the color and you say here, there will be a force perpendicular to the rod, where this is 90 degrees, and the magnitude is unknown. So when you find the magnitude, you will find that it's either positive or negative. If it's positive, it means that this assumption was correct. If it's negative, then you know that the force is actually in the opposite direction. That's what the negative sign is going to tell you. So as we have said, then you, in these initial cases, in all these cases, you have a reaction that it has a known direction, depends on the geometry. What is the direction of the cable? Same here. I didn't discuss this one here. This one is similar to the cable, but the difference is that the cable can only apply tension, only going in that direction, away from the body. This one can apply tension or compression, so it could be, the force can be in this direction or can be also in this direction, right? So, but either way, that doesn't affect your calculations. As I have been saying all this time, if you know the direction, you have to put the direction in the right in the right, in the correct place, in the correct angle. Because if it's known, you have to use that information. If you don't use that information, you're going to get a wrong result. So you have to put the force in the direction that you know it is, and then you will find the magnitude. And if the magnitude was assumed in the wrong direction, then you will get a negative sign at the end when you finish your calculations. So all these supports have known direction. The unknown is just one unknown, is the magnitude of the force, right? You assume the sense of the force in any sense that you want, and the sign of the result will tell you if your assumption was correct or incorrect. If it was incorrect, well, you put it in the right sense for the results. Now let's see the third set of supports. In this set of supports, let's take a look at the first one here. We have this. This is another way to represent the same kind of support, just a pin connection. So if the body tries to move horizontally, this pin is going to oppose to the motion. It's going to apply a reaction that doesn't allow for that motion. So this support will be able to apply force in this direction or in this direction. Let's get one of them. So and the body is not going to move. That legs don't going to move in the direction, in the horizontal direction. And if this body tries to move up or down, the pin is also going to it's not going to allow the motion in the vertical direction. It will oppose to that motion, applying a vertical force. Could be up or could be down. So it could be this way, or it could be this way and this way. Either way, you don't know. You know that there is horizontal reaction, you know that there is vertical reaction, but you don't know if it's to the right or to the left. You don't know if it's up or down. It doesn't matter. You just draw it like this or like this, and again, you do all your calculations, and at the end, if you get a negative sign in any of them, then you know that that one is reversed. So let's say that when you finish all your calculations, you get that the Rx is for example minus 3 newtons. So then you know that this force is not like this, but like this, 3 newtons. So this is a support that has two unknowns, one unknown, two unknowns. Now let's take a look at the rough surface. This is a surface different than this one. This one was frictionless surface. So let me go back to frictionless surface for 1 second. If you have a bar that is on a frictionless surface, no friction, a smooth surface, this floor is able to apply a reaction in the vertical direction like that. But since this is frictionless, there will be no force in the horizontal direction, because if you try to move it in that direction, it's going to move. Nobody is going to apply opposition to that motion horizontally, because there is no friction. So this is only one unknown. Now if you have rough surface, so there is friction, so coefficient of friction different from zero, so friction. So you will have a force here in the vertical direction that is going to oppose to the vertical motion going down, and also you will have some opposition to the horizontal motion that will be the friction force. Let's call it F sub F, frictional force. So there will be two unknowns in that kind of support. And let's see the third one here. If you have this kind of support with a color like that, and there is going on a kind of like a rod here. If this body tries to move along the direction of the rod, it's going to move. because this is a smooth rod, so it's not able to apply force to oppose to that motion in the direction of the rod. So the only force that this rod can apply will be in the direction perpendicular to the rod. If the body tries to move, if the body tries to move in that direction, the rod is going to apply a resistance to oppose to that motion. Or if the body tries to move in this direction, the rod is going to oppose like this. So you have your rod, you have your color there, and then you will have a force in this direction, perpendicular to the rod. So the direction is known and is perpendicular to the rod. Now, what happens if the body here tries to rotate? Well, because of the construction of this color, it's like this is rigid connected like this. It doesn't allow for rotation. So like it doesn't allow for rotation. The rod is fixed and the color has dimensions big enough to don't allow for rotation. So the rod is going to apply a moment that is opposite to any rotation that that element coming from the body is going to exert over the rod. So this kind of support is going to have two reactions. One that is perpendicular to the rod. This is the direction of the rod. So this is 90 degrees. This is the reaction. Let's call it normal because it's perpendicular to the rod. And there will be also a moment that this type of support is going to oppose to the rotation at that element. So this kind of support has two unknowns. So this one has two unknowns, this one has two unknowns also, and this one has two unknowns. They are a little bit different. Let's put it here again, a little better shape. So this one right here, you have the element and it can apply reaction in the vertical direction and reaction in the horizontal direction, but it doesn't apply any reaction moment or moment reaction, because if you want to rotate, since there is a pin here, you can rotate that. If there is a tendency to move in the rotation fashion around the pin, it's gonna happen. There is no construction here able to apply any moment there. Same thing with the rough surface. The rough surface, you have the leg here. The floor here can apply force in the vertical direction. And because there is friction for the horizontal motion is going to oppose to the horizontal motion. So there will be a frictional force opposing to the motion. There will be a vertical reaction. But if you try to rotate, it will rotate freely. So there is no moment reaction at that kind of support. In this one right here, then we have a reaction that is normal to the direction of the rod. So this is 90 degrees. And there will be a moment applied here at the support that doesn't allow for the rotation, right? Doesn't allow for the rotation. So you have two unknowns. In the pin, the unknowns are the component in the x direction, the component on the y direction. Same thing for the rough surface, the horizontal or the force parallel to the surface is the frictional force, and then another force perpendicular to the surface. And in the third one here, the two reactions are one that is perpendicular to the direction of the rod, and the other is the moment reaction. And then there is the last one. This last one the fixed connection here, the fixed support, this fixed support is completely restrained to do any motion. In this kind of support, is completely fixed to the floor or whatever piece is that. So if this element tries to move to the left or to the right, the support is not going to allow it. So there will be a reaction in the x direction. If it tries to go up or down, it's completely attached to the floor, so it doesn't go anywhere. It doesn't go up, it doesn't go down. So there will be a reaction in the y direction. And since you see that this leg is kind of like stacking to the ground, so the ground doesn't allow for rotation, so there will be a moment here that is also a reaction of that kind of support. So this support has three reactions, and those reactions are usually unknown. And if those are the three unknowns that you have in your problem, well, you use your three equations of equilibrium to solve them. All right, so those are the the supports that usually we encounter in the problems of equilibrium of bodies. Well, we have to replace the supports by the equivalent forces in order to do the analysis of the body, right? So let's take a look at how we apply this in a real situation. Let's take a look at this problem. In order to analyze this problem, well, we know that we have our disposal three equations. Summation of forces in the x direction equals to 0. Summation of forces in the y direction equals to 0. And summation of moments in the z direction equals to 0. This summation of moments in the z direction means summation of moments about any point in the xy plane. We are talking about xy plane like this. Okay. In order to do the analysis, then what we have to do is we have to make a drawing of the beam. In this case, we do a drawing of the beam, and we apply all the forces that are acting on the beam. So the forces will be a 500 Newton force here, the force that this cable applies here. This is what we saw before, a short cable. So the force that the cable does is a tension force like this. Let's call it tension at point B. And we know the direction of the cable is at 345. So the direction is known. The only thing that is unknown is the tension, the magnitude. In this case, we even know the sense is going away from the beam. And now this support at point A is what we saw before, is a support that has two unknowns, one vertical, because this beam is not going anywhere in the vertical direction, so there is a reaction here in the y direction, and this beam at point A is not going anywhere in the x direction either, because the support is right there to avoid it. So there will be here another reaction, let's call it Rx. Or another way to call it could be AX and AY. Or we could call it also reaction at A in the Y direction and reaction at A in the X direction. Any of those names is good. The idea is that you have to put a name that it means something with respect to your problem at hand. Then we should put here the dimensions, because they are going to be useful in order to calculate moments. So 3 meters here, 2 meters here. And now that we have this diagram, this is what is called a free body diagram. In a minute or two, we're going to be talking about what we just did and put it in a very organized steps that we have to do in order to analyze these problems. So once you have this situation, a nice diagram with all the forces, then we can apply the equations. Let's do the first equation. Summation of forces in the x direction equals to 0. So you look at all the components in the x direction. In this case will be 1 here, and this one has a component in the x direction that we can draw here. There will be this component here. We can call it tbx, and this one right here tby, right? So we set up all those forces into one equation of components in the x direction. That will be, you also is convenient, you say positive is going to be in the x positive direction. If you don't say anything, we assume that you are using the regular convention that positive is in the x positive direction, but that's not necessarily the case. In some problems where most of the forces are going to the left, well, you can use positive to the left. It doesn't matter. At the end, everything is going to be all right. And if you get one of the forces with a negative sign, you know that that forces was assumed in the incorrect sense. But it doesn't matter the convention of signs that you use. The answer is going to be always the same. Okay, so forces in the x direction. In this case, RAX. Positive. I assume it positive. Okay. What else? Well, this one here, also positive, plus tbx equals to 0. So I know that tbx can be written in terms of tb because we already know the direction of that force. So we have here rax plus tbx is tb, cosine of that angle, so will be 4 over 5 tb, and this will be equal to 0. That's our first equation of equilibrium. Second equation, let's put it here. That's the first equation of equilibrium. Let's put it here like a 1. Second equation of equilibrium. Summation of forces in the y direction equal to 0. I'm going to say positive is going up. So I have this one right here, RAY positive going up, 500 going down, so it will be minus 500 newtons going down, and TBY going up, so it will be plus TBY, and there is no more forces in the vertical direction, so this summation I have to set it up equal to 0 to guarantee equilibrium. So here I will have RAY minus 500 newtons plus TBY that can be expressed in terms of TB will be the vertical component of TB, so it will be 3 over 5 TB equals to 0. Okay, that will be our second equation. And then there will be another equation, summation of moments, so we can do summation of moments about any point. You can choose any point that you want. So what will be a nice point to choose? Usually what you do is you choose a point when you can eliminate as many unknowns as possible. And that point in this case is going to be point B. Why? Because at point B you have one unknown TB completely gone and another unknown RAX. This force RAX goes through the point B, so this RAX doesn't produce any moment with respect to point B. So the only unknown that produces moment with respect to point B is RAY. In that case, that equation is going to allow us to solve for that equation directly. So I'm going to choose summation of moments around point B equals to 0, and I'm going to say positive counterclockwise. So let's see. RAY produce moment with respect to point B in the clockwise direction, in this direction right here, like this, right, around point B. So I have negative RAY multiplied by the lever arm. The lever arm is the distance from the force RAY to point B, which is 3 plus 2 meters, so will be 5 meters. Okay. Now we have another force that produces moment with respect to point B is the force of 500 newtons. That force produces moment in this direction, so it's counterclockwise. So then that moment will be positive, and it will be 500 newtons times the distance, that will be 2 meters. And no more forces produce moment around point B, so this will be equals to 0. So from here we can find reaction AY directly. I will have here that reaction AY will be equal to 502 meters, so will be 1000 newtons meters divided by 5 meters. So this reaction will be 200 newtons. So now, using this value that we just found here, we can plug this value into equation number 2. So now with Ry into equation 2, we will have that Ry 200 newtons minus 500 newtons plus 3 over 5 dB equals to 0. Therefore, dB equals to 5 over 3, 500 minus 200 newtons. So dB will be equal to 500 minus 200 is 300 divided by 3 100, so 500 newtons. And finally, applying this result on equation 1, we can get that Rax plus 45 dB equals to 0. Then Rax equals to minus 4 over 5 dB, which is 500 newtons. Rax equals minus 400 newtons. So we get this negative sign. That means that the assumption that we made that Rax was to the right, let me increase that size here. This assumption was not correct. So we have to make the correction, and we say then that this is not correct. The force Rx is in that direction. So the total result, we can write it like this. Rax equals to 500 newtons to the left. Ray equals 200 newtons. We got positive, so this one was correct. We assume at the beginning that the force was vertical, so it's going up. And moment, and the tension on the little cable TB is 500 newtons. Sorry, this one is 400 here, 400, and the tension is 500, and we got a positive, so is correct in that direction. So this is the answer to that problem. All right. Okay, so let's get into a second problem here. Okay, let's take a look at this second problem here. So what are we going to do here? First, we have to make the free body diagram. And these are the steps that you have to use in order to do a successful free body diagram. Select your system according to your goal. Okay, here we are going to find the reactions on the beam. So our system will be the beam. This will be our system, the beam. So we are going to remove all this stuff here. So once you select your system, you make step 2, draw your system completely isolated. So you draw your beam, completely isolated. Third step, draw the forces and moments. It shouldn't be no parentheses, just as important as the forces and moments that every element exerts on your system. So we erase this support here, and also we erase this support here. You don't see it here, and you don't see it here. So this is not very horizontal. Let me do it very horizontal here, very nicely. Horizontal like this, with the little color there. So since we remove the support at point B, we have to replace whatever we remove in order to leave our system isolated. We remove a bunch of stuff. Every little piece that we remove and that was touching our system is going to be replaced by the force at the point of contact. So there was a force here. This is a roller, so there will be a force here, vertical force, because that roller exerts a force, a vertical force that doesn't allow the beam to go down at that point. So that will be one force. And here on the left at point A, well, there is no vertical force because that's like a free rod that doesn't produce any reaction to the vertical motion, but it produces a reaction in the horizontal direction. So there will be a force here. Let's call it RAX. Well, since there is no y direction, we could call it just RA, because we know that there is no vertical component there, because it's a frictionless rod. Now, but this color there is not allowing for any rotation at that end at point A. So that support is able to apply moment to avoid any rotation. So there will be a moment here. Let's call it M sub A, a reaction moment at A. We don't know the direction, so we just put it in any direction we want. All those three forces are unknown for us, so we know the direction. We know the direction. We might not know the sense. It doesn't matter. You just put it in any sense that you want, and you will get the right sense when you find the sign of the final result. And then what else we have? Well, we have the force. We have the triangular force here. This is the vertical distributed load. That has a magnitude of 200 newtons per meter at the center. right? So that here we are working on this point here. Draw the forces that every element in race exerts on your system. Do not include internal forces. Forces act at the point where the race element touches your system, except for gravity. If there was the weight of any element, the that is a force that in order to apply its effect doesn't need to touch the body. Same way that magnetic forces or forces of that nature don't need to touch the body. But other than that, the elements that were touching your system apply force at the point of contact. What else? Unknown forces, assuming the wrong sense, will have a negative sign when found. We have discussed that already. Here, label each force by its magnitude if known or by a convenient symbol if unknown. This one is the only one that we know, 200 newtons per meter. So we put labels to the forces. This one here on the point B, we should call it R sub B. It will be more convenient to call this R sub B. And the free body diagram must be done very neatly and must be a convenient size so all its elements can be accommodated clearly. I missed this. This shouldn't be in parentheses. Include dimensions. So we have to include the dimensions, 2 meters and 2 meters. When we say include dimensions, you also include any angles that might help to describe the geometry of the system. So these are the steps to produce a good free body diagram in order to set up the right equations to solve the problem. Every problem of this has to have a free body diagram, and you should memorize these steps in order to create a successful free body diagram and a successful solution of a problem. This would be, I think, the most important step. The free body diagram must be done very neatly and must be of convenient size so all its elements can be accommodated clearly. You should be able to see all the dimensions and the location of the forces and the angles of the forces very nicely so you can write your equations without a question, without any ambiguity. So now that we have the free body diagram, then we can set up the equations and solve. Let's proceed with this. The summation of forces in the x direction has to be equal to 0. Forces in the x direction, only RA, so RA, there is no more forces in the x direction, so RA equals to 0. Summation of forces in the y direction equals to 0. Okay, so now we have here, maybe we should do another diagram, or we have to, in order to do the summation of forces, we need to replace this distributed force by a concentrated force that we know how to include in a summation of forces. We cannot include the distributed forces the way it is. And we just learned that what we do is we put an equivalent force that is going to have as magnitude the area of the distributed load and the location, the center of gravity of the distributed load. Since this is a triangle that is symmetric horizontally, so the center of gravity is going to be here right in the middle. So this is where we can put the equivalent force. So we'll have an equivalent force here. I'm going to call it force for the triangle FT. So FT, the force of the triangle will be the area, 1/2 of the base, 4 meters, times the height. The height is 200 newtons per meter. The height is given by this value here, 200 newtons per meter. meters and meters. So this is equal to 400 newtons. And it's located in the middle at 2 meters from either support. So that's the force that we have right there. So the summation of forces in the y direction would be RB going up. Well, I'm gonna do positive going up. So RB going up minus FT going down equals to 0. So RB equals to FT equals to 400 newtons. And now summation of moments. This is actually a very simple problem, so summation of moments with respect to any point will be equally easy. So we have here summation of moments. Let's do moments about any point. Any point will be okay. So let's put summation of moments about the center of the beam. The center line of the beam, it has to be equal to 0. So I'm gonna do positive clockwise. So I have here, I assume moment A to be counterclockwise, so it's gonna be negative here minus MA. Now the moment produced by the reaction RB is in this direction with respect to the center of the beam, so that will be negative also. RB times to 2 meters, this is the distance in order to calculate moments, 2 meters, and there is no more forces applied moments with respect to the center of the beam because the force of the triangle is right there at the point, so the distance will be 0, no moment, so this summation equals to 0. So we have here moment A will be equal to minus RB, which is 400 newtons times 2 meters, so it will be minus 800 newtons meters. So let's put our results very nice. Reaction at A, do a little diagram here with all the results. Reaction at A, we found it to be negative here, so the assumption that we did was wrong, so this was not in this direction, so it was actually this way. So we have reaction at A, moment at A, moment at A, 800 newtons meters. Horizontal force, there is no there. And reaction at B, we got it positive, so it's correct our assumption that is going up. So reaction at B, 400 newtons. So we have reaction at A, 0 newtons. Reaction at moment at A, 800 newtons meters clockwise, and reaction at B, 400 newtons going up. And that will be the answer to the problem. I guess this is also This is also part of the our solution. Let's put it into a rectangle too. Okay, so the procedure, making a free body diagram, steps have to be memorized. Basically, select your structure, then draw it completely isolated from everything else. Remove all the elements that are not included in your free body diagram. Now, every element that you erased was touching your structure or your free body diagram. At the point of contact, there must be a force. So you have to put those forces that include removing the supports and replacing the supports, but the forces that those supports apply on your structure. Putting a label on every force that you draw right there. If you know the value of the force, you put the value. If it's an unknown, you put a label that makes some sense, has some kind of logic with respect to the nomenclature that you are using, the name of the points or whatever, and the dimensions. And it has to be very nicely done with enough size, enough, big enough to accommodate all these elements in a way that you can see them clearly to write the equations of equilibrium. Then to write your equations of equilibrium, and to write your equations of equilibrium, take into account the fact that the summation of moments you can put it with respect to any point that you want. And the best way to is to try to select a point that eliminates unknowns. So a point through which as many unknowns as possible go through that point, so those unknowns don't produce any moment, so they are eliminated from the equation. So you get simpler equation to start solving the equations, and you solve all the equations with all the unknowns based on those equations. That will be very quickly how you how you solve those problems. Let's take a look at another one. Okay, let's take a look at this new problem here. Steps for a free body diagram. First, select your system according to your goal. Here we need to find the reactions. So our system will be our bed bar without the supports. Draw your system completely isolated. So the system will be this bar like this. I'm gonna draw it without the thickness in order to simplify the drawing. This will be 30, 30 degrees. Include the dimensions, so this will be 3 meters, and this will be 4 meters. Draw the forces and moments. So the forces and moments will be first one here at 3, 4, 3, 4. We remove the support at point A, and that support is a pin support, so it has two reactions, one in the vertical direction, let's call it AY, and one in the horizontal direction, let's call it AX. And we remove also the support at point B that is perpendicular to the line. I mean that this line is not very nice, so let's put it a little better. Have to try to do it very nicely here. Ay, ay, ay. Okay, you cannot do it with your hand, you get a ruler, but you need to get those diagrams really nice. Okay, much better. You can even do this one with a ruler. And this one will be nicer with a ruler. formulas here. Okay, you draw your system completely isolated, include all the dimensions, erase the rest of the universe. The forces will be applied at the point of contact with whatever element we erased. If the force is unknown, you put the label. Here it is, the value. And if you don't know it, you just put a name. I am missing the one here at point B, so it will be a reaction like this that I'm going to call RB. And the others I call AX and AY. Unknown forces, assuming the wrong sense, will have a negative sign when found, so you really don't care about in what sense do you put it. Going up or going down, doesn't matter. You try to guess what is the right direction, but it's not really important. Don't spend any time trying to guess the direction of the force. Just put it to the right, to the left, up, down, in the direction that any direction will do okay, as long as the sense, any sense going up or down, left or right, doesn't matter. If you know if this is like a roller here at point B, you know the direction is perpendicular to this line here. That has to be correct. You have to make sure it's 90 degrees right there. The solution of the equation is not going to give you any correction if you make an assumption that is if you make an assumption of something that is known. If it's known, and you have to put the right value. But the other the unknowns that you don't know in what sense they go, you just assume any direction and the sign will correct you if you were wrong. Okay, the labels are there and the free body diagram should be correct. Very, very nicely done, nice size. And then we can proceed to set up the equations of equilibrium. Okay, let's see. You can, instead of setting up, you can do summation of forces in the x direction. Let's do that. Summation of forces in the x direction equals to 0. Summation of forces in the y direction equals to 0. Summation of moments about any point that you wish to find, to choose, equals to 0. So here we could do summation of moments about point A, and we eliminate AX and AY and find RB directly. It will be maybe a matter of getting the components of RB in the X and Y direction like this. RBY and RBX. If we do that, summation of moments, start by summation of moments in the with respect to point A equals to 0. I'm gonna do positive in any direction will be okay. Let's say positive clockwise. In that way, I eliminate these two unknowns from the equation because both of them goes through the point A. So I eliminate the moments of those. So I have one equation on RB and I will find RB directly. So let's try. Let's see. We know that this angle here is 30 degrees. Therefore, this little angle here is 60 degrees. So the component, the vertical component of RBY will be equal to RB sine of 60 and RBX will be RB cosine of 60. And now the distance from these forces to point A in order to calculate moments, you guys have to be very good at that. So I get here the line of action of RBY. So we need to find this distance, let's call it dx. So it will be RBY times dx. And the other distance that we need is this one from here to here. Dy. So the summation will be RBY produces a moment with respect to point A in this direction, all right? Is opposite to what I decided to be positive. So that's going to be a negative moment minus RBY times the distance. The distance will be dx. Dx is going to be 4 meters minus 3 meters cosine 30. 4 meters minus 3 meters cosine 30. Okay? Do you agree? Let me erase a little bit of all this stuff so you can see it better. This distance dx is all this distance minus this distance. Agree? And this distance right here is equal to 3 meters cosine 30. So we have here. So it's 4 meters minus 3 meters cosine 30. That's the moment produced by RBY. Now RBX, this little guy right here, is, we have it RBX, RB cosine 30, and it's going to produce a moment the force goes in this direction, so around point A will go like this, clockwise. So that moment will be in the same direction of my convention of moments. So it will be positive RBX times, we said, dy, this distance right here, which is equal to 3 meters sine 30. 3 meters sine 30 degrees. Agree? Any other force that produces moment with respect to point A? Yes, the 500 Newton force produces moment with respect to point A, and we can make the composition of the 500 force into a vertical component here and a horizontal component here, and we have that this is a 3, 4, 5, so this is 3, 4, 5. So the horizontal component, this horizontal, let's put a label here. Let's call this one F. F equals 500. This will be Fx, and this will be Fy. Fx doesn't produce moment with respect to point A because Fx goes through point A, so there will be zero distance, so no moment right there. The force Fy produce moment with respect to point A, which is equal to the 500 times 4 over 5 multiplied by 4 meters. I hope everybody sees that. Let's put it here very nicely. So the force, the moment produced by the force of 500 newtons is just, if I take it into the components of the force Fx and Fy, Fx doesn't produce any moment because it goes through the point A. The moment will be only produced by the component in the y direction, which will be 500 times 4 over 5. That's the inclination of the force multiplied by 4 meters, which is the distance from the vertical force Fy to point A. That moment is in this direction, so it's the same direction of our convention here. So it's positive, so will be mass plus 500 newtons times 4 over 5 multiplied by 4 meters. We said the other component Fx doesn't produce any moment. So that's it. No more forces produce moment. So we can close our equation and set this equation equals to 0. So we get here what? RBY, which is RB sine 60 minus RB sine 60 times 4 meters minus 3 cosine 30. That will be 4 minus 3 cosine 30. 1.4019 plus RBX, which is RB cosine 60 times 3 meters sine 30, which is 1.5, plus 500 times 4 over 5 times 4, 1600 equals to 0. So from here we can solve for RB, and RB comes to be equals to minus 1600 1600 divided by sine 60 times 1.4019 negative plus cosine 60 times 1.5. This is going to be 30,447.7 positive, meaning that the assumption that we made about the sense of the force RB is correct, so this force goes in this direction. Now summation of forces in the x direction. Summation of forces in the x direction. What forces have component in the x direction? I'm gonna take positive in the positive sense of the x-axis. So we have positive, we have ax in the x direction. We have negative fx. This one is going to be negative fx, which is 500 times 3 over 5. And then we have the x component of RB. That will be negative 2 minus RB cosine 60, which is RB we just found it 3,447.7 cosine 60. And do we have any other force in the x direction? We don't have any more force in the x direction, so this summation is equal to 0. From here we can solve for ax. So ax is gonna be equal to, this is, oh, I have a mistake here. This is not 3, 4. This is 3 over 5. So this is goes to the other side plus 300 plus 17. This comes to be 1723.9. So this comes to be 2024 newtons. All right. Now summation of forces in the y direction. Summation of forces in the y direction equals to 0. Let's do positive going up. What forces go in the y direction? Ay goes in the y direction. This component of RB positive also, so will be RB that we just found to be here 3,047.7 sine of 60, and we have the vertical component of f of the 500 going down minus 500 times 4 over 5. No more forces in the y direction, so this is equal to 0. Therefore, we can get here ay equals to, this goes to the other side, positive 400 minus 2985.8. So this comes to be negative 2586 newtons. So we got a minus sign here. Therefore, this force Ay was not in this direction as we assumed before. So this is not right. It's actually going down. So this is going down like this. So the result, let's put here our final answer. Let's do a little drawing here of our structure, something like this, with a force Ax, a force Ay, and a force Rb, and our 500 force here. So we have Ax equals 2024, going to the right, Ay 20, let's put it three significant figures, 2020, 2590 newtons going down, and Rb 3450 going in this direction. So here we have our nice result here. this problem. Alright, so practice. Doing many exercises. Basically set up a very nice free body diagram with all the dimensions, the forces, completely free from every other element that doesn't have to be in the free body diagram, the labels, and then set up the equations and solve for the unknowns. Alright, that's the way to go.